So good afternoon. I am Amit and I will be talking about spatiotemporal speed of perturbations in a driven dissipative Duffing chain using an OTOC approach. So this work has been jointly done with Professor Anupam Kundu and Professor Manas Kulkarni here at ICTS. So let's start with classical chaotic systems. So we can have a system with very few degrees of freedom, for example, a single Duffing oscillator, a single van der Pol oscillator, or a Lorentz system. And there are many tools to analyze this kind of systems. For example, phase-space portraits, bifurcation diagrams, Lyapunov exponents, Poincare section, and so on. But if we go to systems with many degrees of freedom, they are much more difficult to analyze. However, there exist some tools like time-delayed mutual information, co-moving Lyapunov spectrum, but people are still in search of finding good spatiotemporal measure that can describe the dynamics of a classical many-body system. So on the other hand, for quantum many-body system, regarding scrambling of information and chaos, we have widely used quantities like out-of-time ordered commutators. So this is basically a generic measure of convenient measure of the generation of non-commutativity of initially commuting operators. So a natural question what one might ask is that can one define out of ordered commutator like quantities for classically many-body systems? So in this regard, recently there are some identification of out-of-time ordered correlators in classical many-body systems. For example, Heisenberg spin chain at infinite temperature, classically interacting spins on Kagome lattice, thermalized fluid, obeying inviscid Burgers equation. But all of the systems are Hamiltonian in nature. So the question we are going to pose is that if drive and dissipation are also present in the system, then can one define OTOC-like quantities, and are they helpful for describing the spatiotemporal nature? So to answer this question, we considered this model of driven dissipative chain of coupled Duffing oscillators. So this is the equation of motion where each oscillator is subjected to a double barrel on-site potential. There is dissipation, nearest neighbor harmonic coupling, and a periodic drive. So with a suitable variable transformation, this equation can be transformed into this. So ultimately, the control parameters of the systems are some scaled versions of the dissipation, coupling, driving amplitude, and driving frequency. So the question is then, how can we define out-of-time ordered correlator like quantities for the driven dissipative Duffing chain? So to do that, what we do is to consider two almost identical copies of the Duffing chain at time t equals to 0. By almost I mean that there is an infinitesimal amount of deviation in the initial condition at a particular oscillator. And the question we ask is that how this infinitesimal perturbation, which is initially localized, propagates in space at some later point of time. So to measure this quantity, we define this d, which is a function of both space and time, and the ratio of these two quantities. The denominator is the initially localized perturbation epsilon at the middle oscillator, and the numerator is the perturbation which is gained at a other oscillator I at a different later time tau. Now this quantity can be numerically measured easily from the equation of motion using some initial condition. So now that we have defined this spatiotemporal measure for the driven dissipative Duffing chain, we ask how the space-time diagram of this OTOC gives us information about the dynamical behavior of the Duffing chain. So this is one of our main observations. So through the OTOC heat map, what we observe is that it can have three different types of dynamical regimes. One is sustained chaos, one is non-chaotic regime, and the other is transient chaos. So for sustained chaos, what happened is that the initially localized perturbation at the middle oscillator spreads ballistically in space, grows in time, and sustains indefinitely. Whereas in contrast, for the non-chaotic regime, what happens is the perturbation rather decays. And regarding spread, this initial light cone is formed, but it vanishes very rapidly. Now interestingly, for the transient chaos case, you can see that from both the figures that there is an initial light cone formation. So there is both ballistic spread and growth, but at some point the slope of the cone changes. Ultimately this cone deforms into a complex geometric shape, and the shape of this OTOC actually depends on the choice of the control parameters. So now as you can see that OTOC heat map clearly distinguishes between the three different dynamical regimes of the Duffing chain. Now we will try to extract tools like separate measures of the spatial spread and the temporal growth or perturbation directly from OTOC. So we will define this kind of quantities. The first one is the instantaneous speed. If you see the numerator, what is measures basically is the number of oscillator that have gained a perturbation that is DTH, this DTH times the initial perturbation epsilon. So this DTH is basically some kind of threshold. So the next one is the finite time Lyapunov exponent, which basically measures the growth or decay of the perturbation with time. And there is a third one, which is a velocity dependent Lyapunov exponent. So at large time, what it basically measures is the growth or decay of the perturbation when we move with a velocity v in a frame with respect to the initially perturbed oscillator. So as we have defined these tools for the spatial spread and the temporal growth or decay, now we will go to a particular dynamical regime. So let us first consider the transient chaos case. So in this figure, what we have plotted is the boundaries of the space-time diagram of the OTOC heat maps. So we can divide this heat map in three intervals. One is tau is less than tau star, when tau is between tau star and tau tilde, and when tau is greater than tau tilde. So in the first time interval when tau is less than tau star, what happens is the perturbation spreads ballistically in space. It does not depend on DTH, and from the Lyapunov exponent versus time curve you can see that the oscillators which are inside the light cone have gained positive Lyapunov exponent. But as we are just at the time tau equals to tau star, there is a change in slope. And from the FTLE curve we see that at that point the Lyapunov exponent of all the oscillators that were positive previously start decreasing simultaneously. Then in the next time interval when tau is between tau star and tau tilde, the perturbation still spreads in space but with a less amount of speed. And as we reach tau tilde, the perturbation stops spreading. What happens at tau tilde in case of FTLE curve? The farthest oscillator which has just touched Lyapunov 0 from below starts decreasing. So as we go beyond tau tilde, when tau is greater than tau tilde, the Lyapunov exponent of all the oscillators become below 0 and they ultimately saturate to a negative constant. So the important point is that the transient chaos is actually a dynamical crossover from chaotic to non-chaotic through intermediate complex behavior. And another important point is to note that the number of crossings of Lyapunov 0 in case of transient chaos is 2. So now an important point to note is when tau is greater than tau tilde, the perturbation has stopped spreading and it also decays. So we are eventually going to the non-chaotic regime. And what happens in the non-chaotic regime is that although each of the oscillator is subjected to a double well potential, each oscillator gets stuck near the minima of a single well. So eventually the driven dissipative Duffing chain can be approximated by a driven dissipative harmonic chain. Okay, so this will be more clear from the next slide. So this is the second heat map of the transient chaos. So near this time 200, what happens is the perturbation stops spreading and we are entering in the non-chaotic regime. Now we simulate the system in two different ways. One is directly simulating this Duffing chain, and the next one is by making a harmonic approximation. That is, the Duffing chain is approximated by a driven dissipative harmonic chain, and then we make the simulation, and they match quite well. So in the late time transient chaos regime and in the non-chaotic regime, the driven dissipative Duffing chain can be approximated by a driven dissipative harmonic chain. And since we know that a driven dissipative harmonic chain is just a couple set of linear equations, we can exactly calculate the OTOC, the butterfly speed, and the velocity dependent Lyapunov exponent. This 3/2 exponent coming here will also come for the non-chaotic regime because of the same reasons. Now let me briefly describe the sustained chaos case. So the main differences just I will tell. So the number of crossings of Lyapunov 0 is only once, whereas it was 2 in case of transient chaos case. The boundaries are independent of the DTH value, so we have a constant butterfly speed, and this butterfly speed can be also measured from the velocity dependent Lyapunov exponent versus velocity curve, where The Lyapunov exponent positive means these oscillators are inside the cone. The Lyapunov exponent is negative means that these oscillators are outside the cone. And this slope of the curve, that is butterfly speed, is the point at which lambda v is 0. And another important point to note is that the functional form of the VDLE is very much different from what has been observed earlier for chaotic Hamiltonian systems. So finally, let me go to the non-chaotic regime. So the number of times when it crosses the Lyapunov 0 is 0. The boundaries are very much dependent on the value of the threshold DTH. Only in the DTH going to 0 limit, you can see a ballistic spread and a almost constant butterfly speed. And if you plot the velocity dominant Lyapunov exponent, you will see the same exponent 3/2 as I have explained for the transient chaos case, that the oscillators get stuck near the minima of a single well, and you can approximate the Duffing chain as a harmonic chain. Okay, so let me summarize that OTOC provides a clear description of the three different dynamical regimes of the driven dissipative Duffing chain, which are sustained chaos, non-chaotic regime, and transient chaos. Tools for analyzing the spatial spread and temporal growth separately, we can extract the instantaneous speed, FTLE and VDLE directly from OTOC. And we can demarcate between the three different dynamical regimes just by considering the number of crossing of Lyapunov 0, which is 1, 0, and 2 for sustained chaos, non-chaotic regime, and transient chaos respectively. And in the late time transient chaos or in the non-chaotic regime, you can approximate the Duffing chain by a driven dissipative harmonic chain. The VDLE can have different functional form due to the presence of drive and dissipation. And with the hope that this kind of analysis will help us in future to study generic driven dissipative classical many body systems, I will stop here. Thank you.